Hello. Learning physics becomes easier and interesting if you allow your mind to wander a little bit. Yes, don't stop questions from coming to your mind. Don't think that a question is silly. Allow yourself to think as much as possible and ask questions. But at the same time, don't expect each and every question to be answered by someone else. In fact, you should try to answer most of those questions on your own. Today, I am going to have a discussion on a very familiar system in mechanics, that is a wedge, a triangular wedge, an object having a triangular vertical cross section and a small block placed over it. In all our discussion in this particular video, I will be assuming that surfaces are smooth. This is a very familiar system, no doubt about it, but very few students think a lot about this. In fact, they don't allow their mind to ask many questions to them, and they just accept whatever is being fed to them. So, I'll just demonstrate how you should be literally freeing your mind to think anything and everything. And if you start asking right questions, you will start getting right answers. To begin with, let us assume that this triangular wedge is said to be heavy. There might be some other discussions, some other questions which say that this triangular wedge is fixed. Is there actually any difference between being fixed and being heavy? Not actually. As far as I am concerned, I see that nothing is fixed. It can be heavy, but it is not fixed. What is that? It actually means? This block is heavy compared to what? In the context of our discussion, the mass of this block can be compared to mass of this small block only. There are only two objects given in our system. So when a question reads this is heavy, it simply means the inertia, the mass of this triangular wedge is much, much larger than the inertia of this object. So if you write Newton's second law as F is equal to ma, and you imagine that this mass is large. How large? The largest possible number that you can imagine. So nothing has been given. No comparison sort of thing is there. So question allows you to take this mass as large as possible. So if it is really very high mass, which means even a small amount of acceleration will need some great amount of force to act on this triangular wedge actually. So in absence of any huge force, this triangular wedge will not accelerate. It will not accelerate means it will practically behave as if it is fixed. No, there must be some difference between heavy and fixed. Fixed means this block is attached to this table. It is fixed to the table. So now the block and the table become one unit, and if at all they will move together. But what if table is free to move on the floor? Oh, no. So table is free to move on the floor means actually this wedge is not fixed. No, let us fix the table to the floor of your house. So now it is fixed. This is fixed to table and table is fixed to floor of your house. So it cannot move. It is fixed. No. What if the whole house is allowed to move? If this block pushes it, then this triangular wedge, the table and the house, together they can move. Oh, that is not the case. The house is actually tied to the ground. Tied to the ground. So, this triangular wedge, the table, your house, and the whole earth can be treated as one object which will move together only. How heavy is that? Oh, that's really very heavy. That's really very heavy. But is it fixed? The answer is no. Earth is allowed to move. It is free to move. But in the context of our discussion, the inertia has become so large Inertia of what? The table, the wedge, the table, the house, the earth, everything taken together, because they can move together only, otherwise they will not move. They are tied to one another. So it is very heavy, means you just cannot expect a force to be good enough to give you any appreciable acceleration. So eventually it turns out that if this triangular wedge is heavy or it is fixed, it cannot move. We will take it like that, and therefore this block, small block, is the only object that will move in this particular question. Well, allow your mind to wander a bit. Think, what will happen if this triangular wedge is actually very light? It is having practically zero mass. It is as light as this piece of paper, whereas this block is having a mass of maybe 5 kg. What will happen in that case? This is very light, means again using Newton's second law tells you that if this mass is tending to zero, its inertia is almost zero, it has no inertia, in that case, whatever be the value of acceleration, 3, 4, 5, 9, 10, 100, whatever be the value of acceleration, force will be practically zero. So it means to provide this triangular wedge any amount of acceleration, you actually need not apply any force on it. Even a very small amount of force can give it a very high acceleration. Or you can also say that it is impossible to apply a finite force on a massless object. You cannot apply a force of unbalanced force of 100 Newton on this piece of paper. Can you? Okay, let me keep it on floor. Now you apply a 100 Newton force in horizontal direction on this piece of paper. Can you do that? Of course not. 100 Newton force, how large is it is actually? Think of a 10 kg bag in your hand. How much pain you are having here when holding a 10 kg bag? The same amount of pain you need to experience while pushing this piece of paper. Then only the force on this piece of paper will be 100 Newton. Can you apply? Try it. No, you cannot. For a moment, let us assume that you are successful in applying such a force. Just assume that you are successful in applying such a force, 100 Newton force on a piece of paper which is having mass of fraction of a gram, very small mass. So this force divided by this mass becomes a very large number. Acceleration of this piece of paper will be very high. And if I imagine that you are able to apply this force for even a short while, this piece of paper will attain very high speed. It will immediately, in no time, it will travel a large distance. But how will you travel that large distance to keep applying that force? If this piece of paper, for a moment assume that you are able to apply that force, it reaches the marketplace. How will you reach the marketplace along with this piece of paper? Yes, you can. Provided somebody else is exerting a huge force on you also. So you are pushing this piece of paper and somebody else is pushing you in the same direction, then it is possible that yes, you are able to apply a huge force on this piece of paper. But if there is nobody else, there is no other source of force who is pushing you with tremendous force actually to give you that acceleration, you just cannot apply force on this object. So when the object is very light, well, we can say that whatever be its acceleration, the force on it will be negligible. It will be very small as you can think of. So in this case, this small object will not apply any force on this triangular wedge. In ideal case, when this mass is really tending to zero, there will be no force. In practical life, the force will be small. From Newton's third law, same amount of force will be applied by this wedge on this block. So in effect, this block will experience a gravitational force, that is its weight, and apart from that, it will experience no force because this triangular wedge is pushing it with negligible force. So this block is only experiencing a gravitational force mg. It will have an acceleration g, And as this one moves, it will fall down vertically with acceleration g. So how much will this move? It can have any amount of acceleration, right? So how much will this move? This will move just enough to give this block right amount of space so that it falls with acceleration g. Again, look at the animation. This will move just by an amount which gives this block enough space to fall down with acceleration g. There is no limit to acceleration of this fact, but at the same time, we all understand that this cannot go to infinity. If you imagine that really it moves very fast, it has got tremendous amount of acceleration, then who is even pushing this? So if this triangular wedge leaves contact with the small block, actually nobody is pushing it in horizontal direction. So why at all will it accelerate? There is no question. So it will just move by right amount so that this small block falls down with acceleration equal to small g, right? Okay, come back to our original discussion. This is fixed on this table. It is not allowed to move. Now, where will this block go? It is experiencing only two forces. One is the weight force shown in red color, and the other one is the normal contact force applied by this triangular wedge on the small block. This block will fly away. There is a big normal reaction force. No, it cannot happen. For a moment, assume that this block really experiences a big normal reaction and it has a tendency to fly away. Flying away means the contact between these two objects will loosen. The separation between charged particles will increase. The moment the separation between the charged particles of this block and this triangular wedge increases by a bit, this force reduces. In fact, it will vanish if the separation increases a bit more. So, if for a moment you assume that this triangular wedge will push this block very hard, even a small movement will make that force zero. So after that, this block will be experiencing only a vertically downward force mg, and so it will fall back on this inclined surface only. So the fact of the matter is, in this case, this block is constrained to move along this line. It cannot go anywhere else. It has to move along this line, which implies that the net force acting on this small block has to be in this direction. This small block is experiencing two forces. One is weight and the other is normal contact force, and their resultant will be in this direction. Now suppose that this triangular wedge is free to move. It is having some finite mass. These two masses are comparable. So when this wedge applies a force on this block in this direction, from Newton's third law, this block also applies an equal force in opposite direction on this triangular wedge. This force has a horizontal component, so obviously this triangular wedge will move horizontally towards right in this particular diagram. So if this wedge moves to right, there is a tendency to loosen this contact. The wedge actually tries to move away from the small block. So the contact force gets loosened up a bit. That means this normal force that the wedge was applying on the small block will decrease. So what will happen? If this moves, this normal reaction force decreases in magnitude. This red mg force does not change, but the normal reaction decreases in magnitude. From the law of vector additions, you all must understand that resultant of these two forces will be somewhat in this direction. So if this triangular wedge is fixed, this block is constrained to move in this direction. It cannot go in any other direction. But when the wedge is allowed to move, you can see visually that yes, this triangular wedge is having a net force acting on it in this direction. So it will move in a direction like this. Yes. Many students do get confused. They think that this block will move in this direction only. No, when the triangular wedge is allowed to move freely, you can easily see that this block will actually move in a direction like this. Okay, now some students even think that this block will move like this. If the triangular wedge moves towards right, this block will move like this. This can never happen. This small block can never have a horizontal displacement towards right in this diagram. Why? Because normal reaction, however small it might be, its horizontal component is only in left direction. So this block has a net force in horizontal direction towards left. How can it move towards right? Not possible. So movement of this block can happen in this direction, which has a leftward component, but it can never move in rightward direction. So this is outrightly wrong. Never think like that. Now let us assume that in some time after you release the system, this triangular wedge reaches this position. As discussed right now, this block will be moving in a direction like this. So this block after some time will be here. At time t is equal to 0, you take a snapshot of the system, you get this picture. A little while later, you take another snapshot, and this is the picture that you get. The block is here. It has moved in a direction like this, right? Now, how are the displacements of these two blocks related to one another? It is pretty easy to figure it out. Just for sake of clarity, I will just focus on movement of this point in the small block. Just focus on movement of the red dot. Each and every point on this block move identically. Just focus on movement of the red dot. This red dot, which was originally here, is now here actually. So this red dot has moved a horizontal distance towards left. The wedge has moved a horizontal distance towards right. The distance traveled by this point of the wedge is same as distance traveled by this point of the wedge. It is same as distance traveled by this point of the wedge. This point was earlier here, now it is here. It is same as distance traveled by top point of the wedge. It is same as distance traveled by this point of the wedge. It is now here. So this small block has fallen vertically by some distance. This red dot has fallen vertically by this distance. It has moved to left by this distance, and in the same time this triangular wedge has moved to right by this amount of distance. Let us denote this distance by capital X, that is displacement of this wedge. Let us denote the horizontal displacement of small block by X, that is leftward displacement of small block, and let us denote the vertical displacement of small block Y by Y. What is the relation? If this angle is theta, this angle is also theta, and you can easily see tan of theta is y divided by x plus x. So this is the relations. This is the constraint relation. This is the relation obeying which the motion will happen. This relation cannot be violated as long as this small block stays on this inclined plane. This relationship has to be true. So this is the constraint relation, means this is how the system is constrained to move. This is how the displacements are related to one another. From here on, of course, you can write relationship in velocity and acceleration and all that. For all those calculations and numerical problems, I earlier made a video. I will try to put the link in the description of this video also. You all can watch that. But this video is not meant for that. It is just that we are thinking whatever we can think. And I am very sure, I am confident that many of you are getting many other thoughts as well. Don't wait for me to answer. Always try to answer on your own. Now, let us imagine that this, what happened? Let us imagine that I am there and I am pulling this triangular wedge by applying a large force. I am just trying to drag it out towards right with a very large acceleration. What will happen? Yes, this block will fall down with an acceleration of g. Because if you pull it, go back to the earlier diagram, this one. As I said, as the triangular wedge moves away, there's a tendency to loosen this contact. So if I can drag it very fast, the contact can be lost. If the contact is lost, this normal reaction force actually becomes zero. It will not happen on its own. An external agency is required who can pull this block with very high acceleration in this direction. And in that case, the contact is lost. That means this normal reaction decreases, 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 and becomes 0. Now, this block is only experiencing a weight force, and obviously, it will fall down with acceleration g, nothing else. So, that is what has happened here. So, that is what has happened here. It is falling down with acceleration g when you pull it hard. Now, imagine that I have decided to push this triangular wedge in this direction. I have decided to apply a force on this triangular wedge so as to push it in this direction. So, if I am doing that, what actually I am doing is I am increasing this normal contact force. I am asking this triangular wedge to press this small block even harder. The distance between the charged particles gets closer and the interaction force increases. So, the external agent is pushing this triangular wedge. This leads to increase in this normal reaction. Of course, the weight force has got same magnitude. I am talking about the small block. So, if this normal reaction is quite high, it may happen that resultant of these two forces is in this direction. So, what am I saying? This block will move in this direction. Yes, this is what I am saying. This block will move in this direction. But a little while ago, I was saying that how can it fly? No, it will not fly. It will stay on the inclined plane. But to a person standing on ground, this block will appear to be moving in this direction. So, after a while, when this triangular wedge reaches this position, the small block might be in this position. What do you see now? This small block, which was earlier, the diagram is not exactly to scale. I should have drawn it much closer. This small block, which was earlier here, it has moved up. Yes, from this position to this position. And at the same time, it has moved horizontally from this position to this position. So, this block has covered this much horizontal. This block has covered this much horizontal distance, and at the same time, it has gone up by this much amount of distance. So, yes, this block is moving horizontally in this direction as well as it is going up. But still it is there on the inclined plane, right? It has not left the inclined plane. But visually, suppose that it is a dark room in which this experiment is being performed, and this is not visible, but this is having a glow, some kind of glow, and therefore you can only see this. So, if a person comes and pushes this wedge as described here, what will you see? You will see that this glow of light is traveling somewhat like this. It has moved horizontally as well as it has gone up. So, yes, it can move in that direction only. What is controlling the motion of this small block? Actually, it is experiencing only two forces, mg and this normal force. Mg cannot be changed. We are changing normal force. So, just by changing the magnitude of normal force, yes, you can change the direction of motion of that small block, and that is what is being done here. Now, is it possible that as the triangular wedge moves, when you push it, you are pushing it, this is moving. Is it possible that as the triangular wedge moves, this block does not move relative to the wedge? What does it mean? This small block does not move relative to the wedge. It simply means if this block was placed at this red spot on this wedge, it will always stay on that red spot only. It will appear to you as if the small block has been glued to the wedge. So, is it possible that I push this wedge in such a fashion so that this block appears to be glued to the wedge? Is it possible? Yes, very much. Now, thinking again in terms of forces, I am pushing it so hard so that the normal reaction has increased, mg remains fixed, and resultant of these two forces is exactly horizontal. Well, in which direction this will move is always guided by resultant of these two forces. When this is very small, the resultant can be in this direction. When this is absent, the resultant will be in this direction. When you apply a very large force, this normal reaction is also very large, and as we just saw, this can move in this direction as well. But here, if I control my force, it is very much possible that resultant force acting on this small block is horizontal, and yes, it can move in horizontal direction, which means for a man standing on ground, it will appear as if this small block is glued at this point and it is traveling horizontally along with the triangular wedge. So after some time, this block will be here and it will be on the same red spot. Yes, this is very much possible. Can you write the acceleration of the triangular wedge for this to happen? I'm sure many of you will be able to do that. Please do that on your own. Same thing, a little bit thinking from non-inertial frame. For example, let us assume that this triangular wedge is allowed to move. It is free. We are not applying any force from our side. We just release this system. So this will move in this direction and it will have a movement in this direction. That is for sure, if a person standing on ground is observing the system. But what if there is an observer who is attached to this triangular wedge? Maybe there is a fly sitting on this triangular wedge. What will she see? What will the fly see? How is this small block moving? Forget about small block for a moment. The fly, if you ask the fly, how are you feeling? She will say that a weight force is acting on me. For a moment, let me give a clarification. We will assume that though all surfaces are smooth, but there is friction between the fly and the inclined plane. So fly can remain stuck to one particular point. Okay, if you ask the fly, how do you feel? She will say that apart from other forces, I am experiencing a strange force in this direction. Yes, in this direction. Who is applying this force? She says, I do not know, but I am definitely experiencing a force in this direction. As this triangular, the person standing on ground sees that this triangular wedge is moving that way, the fly feels a force, though she does not know who is the agency of that force. She is, of course, experiencing a normal force, and as I said, there is friction, there is weight, all those forces are there. But apart from that, she is feeling that somebody is trying to drag it away from the inclined surface. Okay, let the fly be a physicist. Physicist? Yes. If you ask the fly, do you see this triangular wedge moving? She will say no, it's not moving. She will say that I am seeing another insect over here and it is at a fixed distance of 10 centimeter from me. This distance is not changing. So I am seeing another insect over here which is at a distance of 8 centimeter from me, and that distance is also not changing. So there is no reason for this observer to believe that this triangular wedge is moving. It is not moving. For this observer, this table is moving. But for this observer, this triangular wedge is not moving. She is physicist. I said, this small block is applying a force on this triangular wedge. This has got a horizontal component. But still this triangular wedge is not moving. Hey, physicist, can you explain that? She says, I don't know, but there must be some force which is balancing this force. She is Newton Bhakt. Bhakt लोगों का तो ऐसे भी जमाना है. She is Newton Bhakt. She says there must be some other force acting on this triangular wedge which is balancing the force applied by this small block on this wedge. Who is applying that force? She has no answer. She is experiencing that strange force on herself. She is experiencing that strange force on this triangular wedge. Oh, I asked her, what about this table? She says table is moving away in this direction with acceleration. Which force is causing that table to move? She says, I don't know. But if it is accelerating, there must be some force acting on it in this direction. So you can see that she herself feels a strange force. She is Newton Bhakt and therefore believes that there must be some force acting on the table in this direction because it seems to be accelerated. She is Newton Bhakt. She sees that this triangular wedge is not moving, though there is a horizontal force acting on it. So C has to conclude that there must be another force acting in this direction. So this strange force, the source of which is not known, is known as pseudo force. So why such pseudo force is required? Why do we need to venture into this reference frame? Why do we need to observe the motion of this small block in the reference frame attached to the wedge? Because of one apparent simplification. In this reference frame of triangular wedge, or in the reference frame of the fly, the direction of motion of this block is fixed. For this fly, this triangular wedge is not moving. It is fixed. I hope you have got that. So to this fly, this block appears to be moving in this direction only. This observer can easily tell you the direction of motion of this block. For an observer standing on ground, it was a bit difficult to figure out because it was moving somewhere here. But for this fly, yes, this is the direction of motion, and this may simplify the problem a little bit. But when the observer is attached to such a frame, apart from all real forces, he must assume a pseudo force. So the fly says that there is a weight force acting on this small block, there is normal reaction force acting on this small block, and then there is a pseudo force acting on this block. This pseudo force always acts in a direction opposite to the direction of the observer. The direction of acceleration of the observer is important. Opposite to that direction, the pseudo force has to be taken into account. Now, these three forces will have a resultant in this direction, because to this observer, this block appears to be moving in this direction only. So these three forces have a resultant in this direction, and that may help you in solving the question in an easier way. Now, if in this reference frame, you know that acceleration of this small block is A, you know the number, you have calculated it, then you can go back to the ground frame and calculate the acceleration of this small block in ground frame. This acceleration is observed by the fly. Now, fly itself is accelerated along with this triangular wedge. So this is acceleration of this small block relative to fly. To that, add the acceleration of fly. Fly means acceleration of this triangular wedge. And resultant of these two accelerations is somewhat in this direction. And this is the true direction of acceleration of that small block. Anybody standing on ground finds the block to be moving in this direction. So students, this is not exactly everything. What I was trying to demonstrate is you can allow yourself to think anything apart from what has been exactly asked in the question. So let your mind wander a bit, and whatever question comes to your mind is a legitimate question. Try to find answer for that. Don't expect all those questions to be answered by someone else. Try to answer as much as possible on your own. And this is the only way how physics can be learned. Thank you and goodbye.